Continuing with 7.3, we're up to number 6. The book does number 6 a little bit differently than I'm going to do it. You can choose the way you want to do it. They both work. But the object here is we've done a letter raised to a number, like x cubed, its derivative is 3x squared. We've done a number, 3 to the x, where we had to use the natural log rule. And now we're going to do a letter raised to another letter. Now the problem with this is you don't know how to integrate with a letter as the exponent, with a letter as the base as well. So the first thing I'm going to do is I'm going to rewrite the f of x as a y. And then I'm going to put a natural log through, because that's the only thing you can do that actually can take care of the exponent issue. Because you have a log rule that says, the power rule that says if you have a power on a logarithm, you can pull the power in front. So it ends up looking like this. Now, we're going to do the derivative, but notice the y is not by itself. So now it's an implicit differentiation. And the derivative of the natural log of y is 1 over y times the derivative of y, whatever that may be. Then, this is a product rule. The first, the derivative of the second, plus the second times the derivative of the first. I need to get y prime by itself, because that was the question, was to find the derivative, and this was part A. So the 1 over y is going to appear on this side as a y. And then the only thing left to do is replace the y by what it was equal to. Right up here at the beginning we said y is equal to x to the sine of x. So y prime is going to be x to the sine of x times 1 over x sine of x plus the natural log of x, the cosine of x. This is exactly the same answer that's in the book. So you can choose either method. Part B says, now that you have that information, figure out what f prime of pi over 2 is. So that's going to be pi over 2 to the sine of pi over 2, 1 over pi over 2 times the sine of pi over 2, plus the natural log of pi over 2 times the cosine of pi over 2. All right, so here the sine of pi over 2 is 1, so this just becomes pi over 2. This is 2 over pi, and the sine of pi over 2 is 1. I don't know the natural log of pi over 2 without my calculator, but the cosine of pi over 2 is 0. So this whole thing turns into pi over 2 times 2 over pi, which is 1. All right, that takes care of example 6. Example 7. It says, finding a horizontal tangent line, determine whether the graph of y equals x to the x, for x is greater than 0, has any horizontal tangent. So the question is there a place where the slope is 0? So I need the derivative. So again, I'm going to stick the natural log through, and this time I'm actually going to pull the power before I write it. This becomes 1 over y, y prime. That says y prime. The first times the derivative of the second, plus the second times the derivative of the first. So this is y prime is equal to, bring the y over, 1 plus natural log of x, which is x to the x, 1 plus natural log of x. Now the question is, will that ever be 0? Well, x to the x, either is this 0? Either x to the x is 0, or the natural log of x plus 1 is 0. Now there is no solution for x to the x, because that can't happen. If you put 0 to the 0 power, that's undefined. So this one doesn't give me any solutions. But when you solve the other one, you get the natural log of x equals -1. Let's put an e through. So x is equal to 1 over e. So yes, there is a spot where there's a horizontal tangent. And if I'm trying to find out the exact point, I would plug that back in. So the y value would be 1 over e to the 1 over e. and according to the book, the point would be 0.368, comma 0.692. So that's the place on the curve where you have a horizontal tangent. And if you graphed it, you would see that that's where it's happening. Okay, in 7.3, before example 8, we've got another derivative rule, and it says the derivative of log base b of x. Now, we just did the derivative of a natural log, and we said it was 1 over x. Well, the same thing happens, but you have to take care of the fact that log base b is in there. It's not a natural log. So the actual derivative looks like this. And they also had a second piece for you that said the derivative of log base b of x, because you've got to guarantee that x is greater than 0, because this appears when x is greater than 0. If you don't have that option, it still turns out to be the same thing as long as x does not equal 0. So it doesn't matter which way you go with this one. Okay, so example 8, part A, wants us to find the derivative of f of x equals log base 5 of 2x plus 1. Okay, so according to my rule, it's 1 over the junk, and then down here there has to be a natural log of the base, times by the derivative of the junk. The derivative of 2x plus 1 is 2. So we end up with 2 over the natural log of 5 with a constant times 1 over 2x plus 1. And you could write that all together with parentheses around the 2x plus 1, but this is how the book left it. The reason that natural log is happening, if you're doing a derivative of the natural log function, it's the same rule. It's just that the base is e. So instead of a natural log of 5 right here, I'd have a natural log of e, which is 1. So it basically is the same rule. It's just that when you're talking about a base of e, it simplifies a little more. Part B wants us to find the derivative of t of n. Whoops. So n times log base 2 of n. Okay, that's going to be a product rule. So t prime of n is going to be the first. The derivative of the second is 1 over n natural log of 2, and the derivative of n is 1, plus the second, log base 2 of n times the derivative of n, which is 1. If we try to simplify this a little bit, the n's are going to cancel, and then here I'm going to have plus log base 2 of n. And they're also pointing out that you could change the bases on this, and you could make it a natural log answer. And what that entails is you have 1 over the natural log of 2, and then you have plus. Change of base formula is ln of n over ln of 2. You take the base and put it natural log of the base on the bottom, and the natural log of the argument, the n, on the top. Then they have the same denominator, and so you could write it like this. Oops, I forgot the plus 1. I'll put it on the end.